Good morning, everyone. My name is Sean Sadler. I'm a third-year student studying civil engineering at KSU. We've been studying architectural forms and structural design. Our group is a large group of undergraduate students containing disciplines of mechanical, civil, and architectural disciplines. We've been studying the use of non-rigid formwork in structural design and structural forms. So here's the problem. Although concrete and other cementous materials contain low embodied energy, because they're used in vast quantities, they make up nearly 9% of global carbon emissions. We use roughly 25 to 30 billion tons of concrete annually, and as an industry, we're trying to reduce our carbon emissions. We've seen methods such as using SCMs like fly ash or slag to reduce the amount of cement that we use in our mix design. For our research, we are planning on taking a different approach, where instead we want to use our material more efficiently by using different forms. In these two images, you see an image that was taken from a construction site in the 1960s and one that was taken only a couple years ago. And I challenge you to spot the difference. Not much has actually changed in our construction techniques, but a lot has changed in the concrete's constituent materials. On a molecular level, concrete has changed a lot, but on the more macro side of things, our shapes haven't really changed that much, and our construction techniques haven't changed at all. We've been prioritizing construction simplicity over material usage. So that leads us to our research goals. For our research, we were trying to define a new architectural language which introduces a coefficient of stiffness into our formworks. By doing this, we're able to integrate architectural forms with our structural needs. So in the top left corner, you see the bending moment diagram that's generated from a uniformly distributed load. By using flexible forms, we're able to place concrete where it's actually needed to resist the moment and remove concrete where it isn't as necessary to have. By doing this, you can reduce concrete usage by about 30%. The beam that we created varies in cross-sectional area along the length of the beam, and it's based largely on three parameters. So firstly, the tension of the fabric, which is based on the material as well as the tension that we place on it, and the hydrostatic pressure that is generated from the concrete, which is a function of the depth. It behaves very similarly to an open channel of infinite length, which is the formula we have in the top left. That's a numerical approximation of the cross-section at a given section based on the tension and the hydrostatic pressure. So our formwork design. For our formwork, we had three parts: the scaffolding, the rigging, and the fabric. The rigging section was two pieces of CNC plywood, which is used to clamp the fabric and force the concrete into the optimized shape that we were looking for. The fabric was then clamped to our scaffolding and was allowed to hang freely and form naturally. The fabric that we used was a geotextile fabric, which the concrete didn't bond to, so we could reuse all the materials many times in many castings. So for our casting, we needed to use a self-consolidated concrete, which means we were trying to get a water cement ratio of about 0.3. We used a high performance water reducer, Sika 2100, and we did this because we needed the flowability to get the effects that we were looking for. So we also used a type 3 cement, and this was due to limitations in our lab. We shared our lab with other students, so because of that, we needed the fast curing time of a type 3 cement. After 14 days of pouring, we then tested the concrete cylinders in a compression test, and we found the average peak stress to be around 8,300 psi. For the beam testing, we decided to do a 4-point bending test. Now, this loading is ideal for us because we're able to have a constant and zero shear in the center of the beam, as well as a constant moment in the center of the beam. By doing this, we're able to isolate the steel and concrete behaviors. The test was performed in a quasi-static manner, where the load was applied slowly and gradually until the beam reached failure. So our beam was originally designed to be a 17-foot long beam, but we had limitations in our lab, so we had to scale it down, and we actually created essentially a model which is only 6 foot long. Because of this, we had to find a different type of internal reinforcement. That was one of our challenges. And the first steel type that we tested was a welded wire mesh. There are a lot of pros to this internal reinforcement. It was very easy to acquire. It was very easy to bend into the intricate shape that we needed. And it had a very high maximum strength. The cons were it was very brittle, and we noticed that there were weak points at the welds. And in a lot of the beams that we tested, the beam would fail at those weld points instead of right at the center. It also had a small cross-sectional area, which means it was just not an accurate model for us. The second steel type, and the one that we ended up going with, was the number 2 pencil rod. This had a lot of advantages. It actually was a consistent material which had no weld points. It was far less brittle and had a much larger ductile behavior. It also had a larger cross-section and was more accurate to the model we were going for. The cons were it had a lower maximum strength, and it was also very difficult to bend. So from like a fabrication perspective, it was more difficult to use. We're also worried about the lack of lugs and deformations in this beam. We were worried that it would cause slipping when we were testing, but because our internal reinforcement went along the bottom of the beam, we just didn't see that. So for the beam's actual performance, we found that the fabric beam did not reach the same maximum strength as the prismatic beam. And this could be seen because of the modes of failure. So our prismatic beam failed right in the center, while our fabric beam failed in the narrow section due to a shear failure. This makes sense because in our design, we didn't include any shear reinforcement for either beams. So that points us to our next steps, how we can reach the same performance. So this top internal reinforcement, that's what we were using for the fabric beams initially. And this is what we're going to test next. It has more shear reinforcement. By doing this, we expect to see the failure mode move towards the center of the beam and achieve a similar strength to the prismatic beam. So for our conclusions, we were able to develop a new formwork system and mixed design for the self-consolidated concrete for the formwork system that we're using. We developed new techniques to cast optimized shaped beams, and the beams that we casted used 30% less concrete. For our next steps, we want to construct a new formwork that will let us have more control over the tension at each of the sections of the beam, which will give us more control over the depth and the cross-section. We'll also have a consistent bearing surface, more beam symmetry, and better reusability. Also with this formwork, we'll be able to investigate the use of post-tension reinforcement from within the beam. And with that, I open up to any questions.